Hello everyone, my name is Junhee Seok. I'm a professor of electrical engineering of Korea University in Korea. This course is about machine learning, especially for data science. Machine learning itself was originally developed in the field of computer science. However, nowadays it comes up with many other fields of engineering and science. Especially with accumulated big data, machine learning has been considered as an essential tool to analyze and utilize this big data. The original machine learning includes many subcategory fields. However, in this course, we will not cover all of these subcategories. Instead, here we will focus on the common area between machine learning and big data science. Okay, so this is the very first video of the first week. In this week, we will go over about the machine learning and some of the supervised learning. Okay. In this week, I will introduce the basic concepts and various types of machine learning. And also, I will introduce some concepts of prediction and inference problems. And here, importantly, I will introduce some of the trade-offs between interpretability and flexibility, as well as between trade-off between bias and variance. Let's see one by one. First, in the machine learning, when you say a machine, it usually means a computer. Some people might think a machine is something like a robot. Usually, a robot has sensors to collect data about the environment, and also it has computers to make a decision, and it has actuators to actually perform something physically based on the decision. However, throughout this course, we will use a machine to refer only a computer that actually make a decision based on the data. An ordinary machine or computer works by predetermined and specific rules in a program. However, there are many cases that predefining specific rule is not that possible, or even though it is possible, it is very inefficient. It's because the environment around a machine can vary very dynamically and unpredictably. In such cases, we need a machine that adaptively works as the change of the environment by learning new rules that are not specified in the program. In other words, instead of a program with a lot of rules, we want to provide a program or algorithm that finds new rules from the data. It's the key of the machine learning. In this diagram, such a machine can be presented as a block that has input, environment, and output of actions. This is a black box. This black box is between environment and action, or we can say this is between input and output. The environment is censored by sensors, okay, and only the sensor data is transferred to this machine, and the action from this machine is the result of the decision. And it is transferred to the actuator and make real physical actions. Anyway, mathematically, a machine can be expressed as a function between input variable y and output variable y and the input variable x. However, there is always errors and noise. So, by the equation, a machine can be expressed by y, the output y is equal to some function f of x plus noise epsilon or E. Y is an output variable that can be used for actual performance. It can be a target of prediction or assigned cluster or reward the machine may get it. X is the input variables that generally describe the environment around a machine. It can be a predictors or observed data or current state and the actions. If this F is already known, it's a program with predefined specific rules. The key point of the machine learning is that this function F is not known. So we need to find this function F from the observed and collected data. The collected data can be both of X and Y or only include X. Depending on the provided data and types of the problem, the machine learning can be further categorized into supervised learning or unsupervised learning or reinforcement learning. So, but commonly, we need to find out this function F. If F, even though we don't know function F, we can model it. The function F can be modeled with a simple linear function, or it can be modeled as a complicated nonlinear form. For example, let's see this the observed data between X and Y. If you want to find function F between X and Y, you may fit this data with a little bit complicated this S shape of curve. This curve looks good. However, for more simplicity, you may want to use simple linear line. Okay? You may want to use this simple linear line because it is easy to express in analytically. Anyway, we want to know or we want to estimate F for the many purpose, but mainly for two problems: prediction and inference. First, prediction problem. In the prediction problem, we want to predict Y, unobserved value Y, through the function F. In order to do this, we first estimate this F function. Here, we use this head notation to indicate the estimated or predicted values. So, this Y is the really observed value, and Y hat is the predicted value. Similarly, this F is the true F. However, F hat is estimated or predicted F for this the true one. So the relation can be expressed like Y hat is equal to F hat of X. Here, Y hat is the estimated value of the real Y. This real Y is actually given as real Fx plus noise. In this prediction problem, the fundamental goal of the prediction is to minimize error between observed Y and the predicted Y hat. Mathematically, it can be written as the expectation of Y minus Y hat squares, or equivalently, because this Y hat is F hat of X, so we can write it Y minus F hat of X. Okay. Before we move further, let's consider why we want to minimize the square of errors, not the square, just the absolute value of error like this. Believe it or not, it is because the square function is easy to analyze and calculate it. In many cases, polynomial functions are easier to handle than absolute functions. mainly because they are differentiable at all points. In old days, without computer, it's a very important merit. So anyway, if we accept this square error, it is easy to show that this expectation of the error y minus y square, it is equal to, because this y is f of x plus epsilon, then this y hat is f hat square. So if you expand this square equation, then we say this the noise is independent to this fx and f hat of x. So we can actually rewrite this equation like this form: expectation of fx minus f hat x square plus variation of epsilon, or error. Okay, so this error term can be separated into two terms. So the first part of the error, this one is the error between true f and estimated f. So if we have a really superpower like a god, we might be able to obtain f hat very close to the true f. So the first term is a reducible error. Extremely, if we can find the exact answer, we can make this error to 0. However, the second part is the variance of the error, which has nothing to do with the estimation of f. So this is a irreducible error, which means regardless of our the power and effort, we cannot reduce this error. So that actually means the actual error can be separated into reducible and irreducible error. So some problems are difficult because it has a big reducible error. In this case, we have a hope that we can actually do better. However, some problems are difficult because of this irreducible error. Then there is actually no hope. There is no way to improve it. Given a problem, it's important to realize that the portion of the reducible and irreducible errors. For example, speech recognition. Speech recognition has been considered as the very difficult problem for a machine. However, actually human beings easily recognize speech, which means the difficulty mainly comes from the reducible error, not from the irreducible error. So we have hope to be better. Okay. Then next is about two kind of prediction problems. There are two types of prediction problems. One is a regression problem, the other is a classification problem. The regression problem is the case prediction for the continuous outcomes. That means when y is the continuous variable, like height or salary or lifespan or and so on. So in this case, for a given data set, the error is measured by mean square error, which is the sample mean of the yi minus yi is the observed value and minus the estimated or predicted value by this estimated function f. The other type of the problem is a classification problem. In the classification problem, y is the discrete outcomes, like the pass or fail or subtypes of the breast cancer or preference to the TV channel. But importantly, this discrete outcome has no order. That's the important point. For example, three classes like the low, middle, and high. These three classes might look like the discrete outcome. However, the problem is they have an order. Okay, but here we are interested in the discrete outcome without such an order, like the man and woman, or color, blue, red, and black. Something like this. So in this prediction problem, our goal is to find out that minimize this MSE, but this MSE is actually measured by, this I is the indicator function, which is I of, let's say, x. This one is 1 if x is true. When x is true. If x is false, this value is 0. Okay? So that means MSE can be expressed in this way. It actually means the error rate. Okay? So MSE is measured in error rate. So that means, in other words, it's measured as the accuracy in the classification case. Okay, so inference is another important problem. Inference is to find significant or important x for y. In the actual data, there are a lot of input variables. Some of them are really important to explain or predict outcome variable y. However, some of them, they are not that important. For example, between height and years of education, which will affect salary more. Definitely, years of education do. Then the question is how we can quantify this importance. There are actually two ways. One is measuring effect size. The effect size is how much y increase when we increase x. Definitely, large effect size means high importance. Another measure is statistical significance, which checks whether x really has an effect on y or not. We will see this. Point later. Actually, how we can measure throughout statistical test. Okay, so anyway, so we want to estimate this function f. In a big picture, there are two approaches. One is parametric approaches, and the other is non-parametric, parametric and non-parametric. A parametric approach assumes a certain types of relation between x and y. Most typical assumption is linearity. For example, we all know that test or exam score is affected by difficulty of the test and the hours of study. But the exact relation is not easy to know. So here we may want to simply assume linearity and model this test score with beta 0 plus beta 1 times difficulty plus beta 2 plus the study hours. We all know that this model is not right, but many people use this approach because it is simple and easy to analyze the result. More importantly, people think there might be no better way. Okay? And another approach is a non-parametric approach, which assumes no prior relations. In this approach, we need to find f that predict y or fit y not much roughly, or not much wiggly. Actually, it might sound nonsense, but actually it is true. It's why non-parametric approach hasn't been used that much, even though with more data and computational power. Okay, so in these days, with more data and more computational power, it's getting easier and easier to apply this non-parametric approach to the data analysis in these days. Okay, so here I will introduce an important concept, the model complexity or flexibility. A model is considered to be more flexible or complex if it can represent a wide range of the functions. For example, when you compare the two linear combination y is equal to beta 0 plus beta 1 x, and compared with this model with y is equal to beta 0 plus beta 1 x plus beta 2 x squared. This second model is has more flexibility, or more flexible, or more complex, because second model can include any model of the first model. Okay, so this is the concept of the model flexibility. So generally, a neural network is more flexible than a linear model. And there is the many such cases. Here is a trade-off between this flexibility and interpretability. In this toy example, you may want to use this S shape of curve to fit the data, or simply you may want to use this linear line. Okay? Definitely, this S shape of curve is more flexible than this linear line. However, in terms of flexibility, for example, if we want to answer about the effect size, which means when x increases 10%, how about y gonna increase? Okay. For such a question, you can answer simply with this linear model, because the increase rate of y, they are all the same over the whole range of x in this simple linear model. However, in this the complicated model, the rate actually changes, so it's not that simple to answer. So this model has the less interpretability. Generally, there is a trade-off between flexibility and interpretability. If we increase flexibility, we have to sacrifice this interpretability. Simple models have high interpretability, but they cannot model the complex relations. Usually, linear models has low flexibility and high interpretability. However, neural net or support vector machine, they have the high flexibility but low interpretability. Neural net, something like the deep learning, they have the really high flexibility, but they have a very low interpretability. Okay, so this is the end of the first section. I'm going to stop here, and I will discuss more about this machine learning stuff in the next session. Thank you very much.